Good evening, everyone. We are very pleased to join by another great personality working in quantum field, Mr. Jyotishwaran CA. He is a PhD student at IIT Roorkee in the Department of Electronics and Communication Engineering. His research focuses on quantum computing, quantum algorithms, and fundamental problems in quantum mechanics. He has also published several peer-reviewed research papers in the related areas. So over to you, Mr. Jyotishwaran.
Yeah, hello everyone. So, welcome to the session today. Let me share my screen. Uh, my slides visible?
Yeah.
Yes, it's visible.
Basically, they are not allowed to like unmute, but if they will raise the hand, so like we will confirm you like if some issues there.
Yeah, sure.
Okay. Yeah, it's
All
visible.
right.
Yeah.
Yeah, so I was contacted by Sumit, I think, last week, and he told me to take a session dealing with the very basics of quantum computing. So what I'm going to try to do today is I will talk about, like, I will try to keep the mathematics as far away as possible. By that I mean I will give you the results, but I will not work them out, and I will not give too many results. So whatever is given, you can take it for granted. Some of the things should be intuitive. The rest you can, accept it. It's fine. And later on, as you study further and further, things ought to become more and more clear. So, in preparation for this session, what I was essentially looking at is like what should be the one thing that I should talk about, so as to make my audience understand about the power of quantum computing. What should be the one thing? So I went through a mini, a list of phenomena and properties that one observes in quantum systems, and finally I decided that I will not talk much about any of them. Instead, I will talk about a very mathematical property. That property is linearity. So, what is linearity? What context am I talking about linearity in? Is what we shall look at today. So, I'll try to spend around half an hour on this, and then the other, assuming we are also taking time for questions, I will say that I will finish my talk in around 50 minutes. So, I'll say take close to half an hour on the first part where I discuss about linearity as a phenomena in and of itself, and then I will spend the remainder of the time discussing three quantum algorithms. Again, I'm not going into the quantum circuits. We are not doing the mathematics. I will give you an intuitive idea as to how this principle of linearity plays a role in, or rather enables, a quantum computer to solve these problems. And with that, we'll end the session. I'll take some questions and whatnot. Okay, so let us begin. Yes. So first, a glossary of topics, glossary of terms. So first and foremost, we have what is called a bit. A bit is short for a binary digit. It is a number that takes only two values, 0 and 1. And a bit of an unknown value, I will call a Boolean variable. Alternatively, a bit is also referred to as the most fundamental unit of classical information. And again, it takes only two values, 0 or 1. Now, a Boolean function is a function of one or many Boolean variables, essentially one or many unknown bits. And Boolean functions are constructed using the classical logic gates. Here, let me just add that here. Classical logic gates. Let me also parameterize it, or rather, no, when I say logic gates, it's understood. So yeah, let's leave it like this. And then we come over to qubit, which most of us should know what it is. It is the fundamental unit of quantum information. It is essentially the quantum analog of a bit. Now, about a qubit, I will not say much. I will only say two things. First and foremost, the quantum bit or qubit can exist in infinitely many states. Even a single quantum bit can exist in infinitely many states, but we can observe it in only one of two states. So when I try to observe my quantum bit, it is going to appear in only one of two states. Which two states? What are they? I'm not going to talk about them. They are not of particular interest to us in today's discussion. And then finally, we have this thing called measurement. And this is the only known method to extract information from a quantum bit, from a qubit. Like measuring a single qubit, quantum bit yields a single classical bit of information. So that is where this whole two states thing comes from. And the act of observing, so when I said it can be observed in only one of two states, I mean if I perform a measurement, I can observe it arriving at one of two states. So the act of observing a qubit state is performed through a measurement. So these are the words that I may use, and for the context of today's discussion, it is enough if you remember these terms, like these meanings for these terms. So let us talk about the qubit state very quickly. Now here, you can just take it for granted. I may be missing some of the things, I may be skipping. So people who are more technically equipped, I noticed one or two names that I'm slightly familiar with in the list of attendees. So if you have listened to anything that I've spoken about before, you'll see that I'm skipping some details. Don't worry about it. Okay, it's fine. So the state of a single qubit can be represented as a vector like this, a column vector A and B. What do I mean by a vector? A vector is just another word for a matrix, or it's just an object where I define it as a column arrangement of two numbers A and B, and these numbers A and B are complex numbers. And then what I'm going to do is I'm going to borrow some, a little bit of mathematics from, say, something like 2D geometry, coordinate geometry. At least I can hope that everybody knows that much mathematics. And I will write AB, this column vector, as A times 1, 0 plus B times 0, 1. Here, multiplication is like intuitively defined. I'm not formally defining the vector scalar multiplication of a vector. I'm just saying A times 1, 0 is going to be A into 1 into A into 0. So that is A0. And B times 0 into 1 is going to be B into 0 times B into 1, which is going to be 0B. And the resultant vector we can see is the column vector AB. Now what I'm going to do is I'm going to set up this equivalence right here. So I am saying that these two things are equivalent to each other. So whenever I have this column vector 1, 0, I will write this as this symbol here, and whenever I have 0, 1, I will write this as this symbol here. These terms are read as ket 0, ket 0, and this I can read this as ket 1. So ket 0 and ket 1. Again, this notation is from almost 100 years ago. This is due to Paul Dirac, one of the founding fathers of quantum mechanics. Why am I using this? Well, for people who have used this, you'll know why I'm using this. For people who are not familiar with this, as things progress, maybe if not now, a couple of months down the line, you'll realize that this is the easiest way to handle these objects. Like, this makes the mathematics very straightforward. In fact, it makes it very intuitive and easy to understand. Alternatively, I can perform all of quantum computing using these column vectors itself. I don't need to use these, but using this gives us some further benefits down the road. And since this is supposed to be a sort of an introductory session, I will use these symbols. Now, these two states, ket 0 and ket 1, are known as the basis states of the qubit. Now, what is a basis? Essentially, what it is every single qubit state, AB, can be written as a combination of these two vectors. Like, if I need any two complex numbers here, I will be able to split them, decompose them, and write them as A times 1, 0 plus B times 0, 1. So that is why I'm calling this a basis, calling these two states the basis states. And performing a measurement of some kind, I'm not specifying what kind. Let me also mention that here, that this measurement is very nondescript and non-specific. Essentially, when I say measuring, in some way. Because to talk about how I'm measuring a qubit, I will have to talk about the physics of the qubit. Now, we shall not be doing much physics today. Maybe some other day. So it will yield a resultant state Ket0 with probability mod A squared. So this quantity mod A squared will be defined as, so I will write this here, mod A squared is equal to A times A bar, where A bar is the conjugate, complex conjugate. Conjugate of A. And it is things like this that kind of creates an entry barrier for quantum computing, because although any of us who's gone through a good high school education will know what complex numbers are, the point is, since we don't use them all that much, people tend to forget. So, but if one remembers what complex numbers are and what these quantities are, and for any complex number, I can be guaranteed that this product will always give me a positive number. If A is equal to 0, then this is going to be 0. Otherwise, it's always going to be a positive number. And similarly, I will get Ket1 with probability mod B squared and mod B squared. Similarly, can be defined as, and simply just write the expression. I will not clarify the notation. And since these are the only two outcomes, going back, sorry, I went forward instead of going back. Remember, it can exist in infinitely many states, but observed in only one of two states. So I'm either going to observe it in Ket0 or I'm going to observe it in Ket1. So these are the only two possibilities, which implies this is my entire space of events. Therefore, the probability of getting Ket0 and the probability of getting Ket1 should be equal to 1. So this is known as the normalization rule or the normalization criteria. And it can be shown that there are infinitely many such A's and B's. In fact, given an A and B such that mod A squared plus mod B squared is equal to 1, I can very quickly say that from this, let me use a different color here. From this, if I'm being a little bit creative, I can say BA is also a valid single qubit state, because exchanging the position does not change this normalization rule. It holds. And then I can also say A minus B is also a valid state. Alternatively, I can say B minus A is also a valid state. So given a single A comma B, I can define 3 other states. So, and there are many other ways to define these coordinates of this vector, or the entries, the values of this vector, the entries in the column vector. And so there are infinitely many such pairs of A and B. That is why I said a single qubit can exist in infinitely many states. It is a rather complex, complicated object. Now, where does linearity come into this picture? Every single qubit state can be written as a combination of the two basis states. I didn't need two offs. Combination of the two basis states. Now, this should be obvious from here, but if it is not obvious, just take it for granted. You can trust me on that. After all, I mean, the organizers of this event have enough confidence in me to invite me to give a talk, so you can trust me that I'm not misleading you here. Therefore, every single qubit state is a linear combination of the basis state, and this is where the linearity entered the picture. So every general quantum state is always going to be a linear combination of two basis states, if I'm talking about a single qubit. And manipulating these linear combinations for single or multi-qubit states is at the heart of quantum computing. Like virtually all of quantum computing is me figuring out ways to do this, to manipulate the values A and B. That is the only thing that I want to do. Okay, and these manipulations are performed through objects known as quantum gates. There are many quantum gates. We shall be looking at only one for this session. Since I have only an hour, there is only one that I can do any justice in discussing. And every quantum computational algorithm that I'm referring to, the reason I mentioned computational here is these days there are many more quantum processes through which we can do some information processing, but not all of them utilize these quantum gates. So when I say quantum computational algorithm, I'm talking about quantum algorithm that use quantum gate operations. So every quantum computational algorithm can be represented as a sequence of quantum gate operations. It can be a single qubit operation, it can be a many qubit operation. There are many such possibilities. Now, what are these quantum gates? Now, given that I have mentioned a qubit state can be represented as a vector, I'm just saying a single qubit quantum gate is given by a 2 cross 2 complex matrix. Essentially, it is a quantum gate G can be written as A, B, C, D, where I am telling you A, B, C, and D are complex numbers. There is obviously more to this, but for now, it is enough if we take this. Now, every quantum algorithm that we are going to consider today uses this following gate. I'm going to call this gate H. In fact, I will try to finish the entire session without naming this gate. It's like a self-imposed challenge. So this H gate is defined by this matrix. Like 1 by root 2, I've taken out as a common factor. Otherwise, I can, alternatively just go ahead and write it like this. It's going to be 1 by square root of 2, 1 by square root of 2, 1 by square root of 2, minus 1 by square root of 2. So this is another way of writing this quantum gate. And this gate performs the following operations. Essentially, when I say H on kit 0, what I mean is, remember this is a matrix and this is a column vector. Now let us add some dimensions to this. This has 2 rows and 1 column, so this is a 2 cross 1 column vector. And this matrix is known to be 2 cross 2. So from here, I can directly say that a 2 cross 2 matrix multiplied by a 2 cross 1 matrix will give me a 2 cross 1 matrix. So this is matrix multiplication, high school mathematics. So from this, I can say that performing this multiplication gives me an object that resembles a quantum state. So I have ket 0 plus ket 1 by root 2. Again, here I am assuming some things intuitively. This can alternatively be written as 1 by root 2 ket 0 plus 1 by root 2 ket 1. I can write it as this. Since I can write it like this, the eagle-eyed observer among you will notice that these are the values of A and B. And from this, since this is a real number, the conjugate of a real number is itself. So I will have 1 by root 2 into 1 by root 2, which is mod A square, which is 1 by 2. And B is the same as A, therefore that is also going to be 1 by 2. So mod A squared plus mod B squared is equal to 1. This is a valid single qubit state. Now remember, I told you, if AB is a valid single qubit state, then A minus B is also a valid single qubit state. And that is what we have here. I have 1 by root 2 and minus 1 by root 2. So this gate performs these two operations. If my initial state is in ket 0, then I will get this state. 1 by root 2 ket 0 plus 1 by root 2 ket 1. If my initial state is in ket 1, then I will get this state. 1 by root 2 ket 0 minus 1 by root 2 ket 1. So this gate creates a linear superposition. Essentially, when I say superposition, what do I mean? I only mean combination. That is all. This is just a fancy word for combination. I'm just adding these two vectors. I'm just, what I did here, this is linear superposition. That is all. Okay. So this creates a linear combination state out of a base state. So that is one thing that this gate does. And for some reason, this is, my aim is to explain that reason well. This gate becomes extremely essential for like virtually all of quantum computing or quantum information processing of any kind. So if I do my job well at the end of today's session, you will all get an appreciation for this particular gate, the H gate. Okay. Now, linearity and quantum gates. Now, any operation that I can represent as a matrix is linear by definition. So, again, take this as granted, but this essentially comes from the subject of linear algebra. So, any operator any operator or operation that I can represent using a matrix is linear by definition. Now, what is the linearity here? The linearity is as follows. Let us say I have a general state A ket 0 plus B ket 1 and I apply the H gate on it. What will I get? What I will get, I can write directly like this. Like one thing that we can do is we can take this matrix and we can multiply, this is equivalent to this. I can just take this matrix 1 by root 2, 1, 1, 1, minus 1, and then I can multiply it with AP, perform some matrix multiplication. And I will get some answers. Alternatively, I can leverage this notation. So here, since H is linear, what is going to happen is this is going to act individually on both the components. That is what we call a linear system. Like if I have an operation and I have a linear combination of two inputs, then the operation is applied equally to the two inputs. So let me quickly just jot that down here. So I'm talking about linearity. I mean a linear operator applied on a linear combination of inputs acts on each input separately. Have I done this correctly? No. Separately. No. I think it is a linear. You know what? Just spell check separately. For some reason, I seem to have forgotten spelling. So what I need to do is I just need to act H on ket 0 to get A times ket 0 plus ket 1 by root 2. And I will act H on ket 1 to get B times ket 0 minus ket 1 by root 2. And then I can rearrange the terms. I will get A plus B by root 2 times ket 0, A minus B by root 2 times ket 1. Interested parties can perform the matrix multiplication on this and get the same values. And this is one of the advantages of using the Dirac notation, the ket notation. I didn't have to perform any matrix multiplication. All I'm doing here is addition and rearrangement. If I know these two results beforehand, which I have given here, then this operation can be resolved without performing any matrix multiplication. And in fact, if we are talking about a quantum computer, the operation happens naturally. Like, there is no. I will come to the natural part in a bit. You know what? Just put a pin on that. Now, okay. I think while rearranging the slides, I forgot to remove this. You know what? I'll come back to this last statement in just 1 minute. Let us talk about Boolean functions first. Now, just to quickly go back to the very beginning, A Boolean function is a function of one or many Boolean variables. Boolean variables are essentially unknown bits. And Boolean functions are constructed using classical logic gates. That's what we know. So that is all we will need. Boolean functions are of fundamental importance to computer science. How are they? What is the importance? Every deterministic classical computation or algorithm can be represented by a Boolean function. The deterministic thing is a condition that we need. Like if I have a fixed algorithm where I'm not varying the operations too much, or I'm not varying the operations at all, then that entire algorithm can be represented by a Boolean function. Every single operation our smartphones and our computer performs, a vast majority of them can be represented as Boolean functions. Most of the operations any digital device does can be represented as a Boolean function. And Boolean functions are also important for determining the hardness of various computational problems. Like essentially, since every computation or algorithm that I'm performing can be represented by a Boolean function, the hardness of the problem associated with the Boolean function will tell me how hard the algorithm is to implement. I'm not going into further details here, but you can just consider this hand-waving argument of mine. So Boolean functions are actually essential for determining the hardness of many computational problems. So in that way, to the discipline of computer science, like Boolean functions lies at the very center of it. Okay, and now a little bit of math. A Boolean function defined over n input variables. If a Boolean function has n input variables, then it will have a total of 2 to the power n possible output variables. You can take this for granted. People who know why this is so, you already know it. I don't have to explain it to you. People who do not know this, just take this for granted. Now, this is the point. It is possible to implement any Boolean function as a quantum gate. This is a very important fact. Any Boolean function that I have, I can represent as a quantum gate. Like through a sequence of elementary quantum gates, I can create a more complex quantum gate. And this allowed for the development of the very first quantum algorithms. So we are going to be looking at one or two of them now. Yeah, I'm on schedule, more or less. So, So Boolean functions can be implemented as a quantum gate, and this allows us to develop algorithms. What kind of algorithms? We are going to see in just a minute. Yes. Now let me quickly make some remarks on n-qubit states. I'm not going too much into the details. I'm especially not going into how to construct the basis states. I'm just giving it to you. And for the purposes of today's discussion, I will not be using anything more than 3 qubit states. So you can rest assured, whatever I'm mentioning here, you can just take it for granted. Let us say I have a system of n qubits. This n qubit system has 2 to the power n basis states. Just like for a single qubit system, I had 2 basis states. So when n is equal to 1, I had 2 to the power 1 basis states. And when I have n qubits, I will have 2 to the power n basis states. Each can be identified using a unique n-bit string. How many n-bit strings do I have? I actually have 2 to the power n-bit strings. So for instance, the 3 qubit basis states are given by this. I can write it as ket 000, ket 001, ket 010, ket 011, ket 100, ket 101, ket 110, and ket 111. So these are 8 unique n-bit strings. None of them are equal to each other, and there are only these 8 possible strings. And every 3 qubit state is a linear combination of these basis states. Okay. So, and let us say we start with the 000 state. And what I'm doing is now, since this has 3 qubits in it, what I'm going to do is I'm going to apply an operation that I'm going to call H3. What does H3 mean? I will show you during the demonstration. Essentially, I'm applying the H gate to each qubit separately. Yeah, I think this is the spelling for separately. I was right. Yes. So one gets the following state. Now, what do I get when I apply the H gate to the 000 state? I will get a linear combination of all the 8 basis vectors with equal superposition coefficient. Essentially, this will have 8 coefficients, A, B, C, D, E, F, G, H. All of them are equal to 1 over root 8 or 1 over 2 root 2. And once again, you can see that if I take the mod square of 1 over 2 root 2, I will get 1 by 8. And if I add it 8 times, I will get 1. So this normalization rule that I mentioned way up here is actually true for multi-qubit states as well. Okay. So I will quickly write that down here. The normalization rule applies to multi-qubit states as well. Okay, so this is the primer. This is what we need to do the rest of the session's activities. Let me just see.